Hello everybody, so today I will do the system design of WhatsApp game. So I will do the deep dive today. So yesterday I took the same video, but I will do the same thing today for my practice sake. So today's topic is these two things. Number one is scalability, and then I will talk about how I can support multiple devices for the same user. It's a kind of follow-up question I like. That being said, I will get started with scalability. Okay, so scalability wise, I have the non-functional requirement here, 1 billion daily active users. So I will discuss the scalability based on this number. So I will start with the back of the envelope estimation. So yeah, I will discuss the scalability from two perspectives. So number one is the throughput. Then number two is storage size. So let's say there are 1 billion active users. So in terms of this throughput, here we have some APIs, including Create Chat API, Real-Time Message API, and this is a WebSocket, and this is the S3, Upload, Download Media, and there is a Bulk Fetch API, and okay, so this one, I've already moved it to the WebSocket, so I don't need it anymore. And that being said, I'd like to talk about this API, real-time messaging API, because let's think of the Create Chat API. The frequency for the user to call this API is lower, much lower than the messaging API, because this is created only when the user makes a new chat. And how often do users make a new chat? Maybe once every week or something, from my experience. So this is quite low, heavy loaded. So I'd like to focus on more on this one, WebSocket connection. And also upload media, download media, this is S3 API. And S3 internally scales infinitely. So based on the object key, it does consistent hashing to scale out internally, which means that as long as we don't make the request to specific object key so frequently, it will not become an issue. And the same file, the file is downloaded, only by the user who were in the same chat room, probably 1 or 2 or 3, up to 100. So these S3 APIs are, I can assume these are fine with heavy load, or I should say these are not heavy loaded. And for this one, yes, this one is a bit of a concern. So this is used, or I should say, called when user becomes online. When user becomes online, this API is called once. So how often does user online? So how often do user open the WhatsApp in a day? Probably once every hour or something. So I will, talk about this API later with that rate. Okay, for this one, real-time messaging API. So I have to think how many users are available, or just say online, in each time. So how long are the users online in the WhatsApp, including the background, I mean, running, including it is running in the background. So I will do this estimation as around a few hours a day. So for each user, 10% of the time in a day, they are online, which means that there are 100 million users online at the same time. Okay. So, which means that 100 million users are connected to the real-time message service. This is obviously not handleable by one server because each WebSocket takes 10 kilobyte. So now I will do this measure for each server can hold how many WebSocket connections. Each WebSocket object is like 10 kilobyte on memory. So assuming there are 250 gigabyte of memory, how many WebSocket are stored in the one physical device, or I mean physical server, is so 250 million divided by 10, which is 25 million WebSocket per server. This means that we need 100 million, 25 million, so 4 servers, not so many. So we need 4 real-time message service server, physical server. Including some buffers, I can say we need 10 servers. Of course, if there is kind of user surge, we can scale out the server and increase the number of users who can connect to this service. But basically, 10 servers are the necessary, I can say. Okay, so we need 10 servers, so we scale out. But the problem here is, let's say there is a user who is in the chat A, and he belongs to he is connected to the server 1. And let's say there is another user who is in the same chat room, who is connected to a different server 2. In that case, on this server, it cannot deliver the message to the second user's WebSocket connection because they are on a different server. So I have 2 solutions here. So number 1 is try to make sure that users in the same chat are connected to the same physical server. And the second solution is kind of send the message across servers, like server 1 to server 2. So both of them works, but I would go with the latter approach because if I take the first approach, it means that each request becomes a kind of state. If I do that, I have to use a kind of consistent hashing to make sure that which server is connected to which user is connected to which. And the difficult problem here is because we use the hashing, if some server fails, we have to make sure that those connections are connected to other server correctly, or I should say, which means that the rehashing is so hard. Or I should say, if there are so many users are connected, and we'd like to increase the number of server, we have to rehash and then move the existing connection to another server, which is definitely kind of tough to do this migration. So I don't take this approach. Instead, I use Redis pops up here. So what happens is that each server sends the message he received to Redis PubSub. This is a kind of queue, and this Redis PubSub sends a message to another server, and in this way the message is delivered to the other servers. And I will be more specific what Redis PubSub is from now. So Redis PubSub is like the queue, like Kafka, but the biggest difference from Kafka is the message is not stored in the disk. So the message is stored in the memory. And Redis PubSub takes the fire and forget approach, which means that Redis PubSub pushes the message to the subscribers who registers the subscription, in this case real-time message server, and Redis PubSub sends a message when it receives the message from a publisher. But if the request fails, if the subscriber is not available, it completely forgets, and Redis PubSub never retries the message. So that's why it's called fire and forget. And that being said, yeah, I would use the Redis PubSub here because, yeah, even though there is a kind of, shortage, disadvantage in the durability, it's really low latency because it stores data only in memory. So this is important here because as we specified here, so we have to deliver the message within 500 millisecond. We really need the low latency in this design. Okay, and that being said, if the Redis PubSub is down or the server is unavailable, user fetches the message which has not been delivered with the bulk fetch API, receive pass messages API. Yeah, this is a kind of, of course with this, there should be some delay until the message is displayed in the UI. But yeah, still, I think this is an acceptable kind of trade-off for the low latency with Redis PubSub. And now we have to create the topics here. So I can say we use one topic per one chat ID. So for each chat, the message, one topic is created. So each message is sent to the topic, queue, corresponds to the chat ID. Yeah, and when the user connects to the real-time message service, this checks which chat ID he is interested in, and for those topics, it subscribes. And of course, we can do the kind of scaling out with Redis cluster here. I can think that each topic is completely independent, so scaling out completely works. Yeah, and also I can say, this topic is actually the kind of namespace. So this means that this doesn't mean that each server connects to each topic. Different, network. Different subscription. If this server this server makes a subscription to one instance of Redis cluster, it can specify multiple topics to hit right to subscribe. So yeah, what I mean to say is this server doesn't make so many connection with this. So this is only, number of server. So sorry, number of instances of Redis cluster. Oh, and also I have to clarify something. So here, between this Redis message server and Redis PubSub instance, the TCP connection is kept alive. So as long as the network capacity allows, so many messages can be sent to here. So I mean, in this kind of subscription, yeah. So, but of course, if the CPU boundary hits, I mean, this server's CPU boundary becomes the issue, we can scale out. Yeah. So I don't do any more calculation, but these can be scaled out independently if there is a kind of bound for each. Okay, so these are, what is it? So about the discussion of the WebSocket. Now I will talk about, oh, by the way, I talked specifically about these two places, but of course for API Gateway, this scales out internally because this is internally the cluster of servers, and for message service and chat service, both of them are state REST API. These two services provide only state REST APIs. They can scale out independently. Yeah, and that's it. Okay, so now I talked about upload media, real-time messaging API. Okay, now we'll do the quick estimation on receive pass messages API. So here. So let's say user makes a request 10 times a day. So in that case, 10 billion users make 10 times request per day, and 1 day is 10 to the 5 seconds. So 1 billion is 10 to the 9. So 10 to the 10 by 5, so that's a 5. So this is 100k requests per sec. So with this request, this message service is loaded with this throughput. So as I said, this server layer, application server layer can be scaled out. So there's the problem. Here, message DB, this is kind of tough. He tries to, each request tries to fetch the message from message delivery. And yeah, but the good thing is I set the primary key to user ID. So internally in DynamoDB, the servers are scaled out and only the message delivery records which belong to the same user are on the same server. So each server node, I can say, experiences only 10 requests per day, theoretically. Of course, I know that in AWS Dynamo, carrying out, or I should say, node is kind of virtual node. So one physical server may include multiple nodes, but as long as, but still, DynamoDB automatically, internally, moves the virtual node to one physical node if that virtual node is very heavy loaded, or I should say, it has so much storage size of data. So I can think of that in the worst case, in the very heavy loaded case, only message delivery records belong to the same user is on the one server. And of course, we did here redundancy here. So we don't have to take a look at message record anymore. So this is, this works completely. Okay. So now I've talked about the throughput. Okay, so the next discussion is about the storage size. So I will take a look at this PostgreSQL. So number of chat and number of user chat relation. Obviously, user chat relation is the biggest table because how should I say, one chat belongs to at least one user, and one user is joined by at least two users. Sorry, one user belongs to at least one chat. So this I can say this user chat relation is bigger than chat table and bigger than user table. So I will take a look at this table as the biggest tables. Sorry, I will take a look at this user chat relation table because this is the biggest and the biggest concern. So let's assume one user has 10 chat spaces, and we assume that there are 2 billion users. Let's say half of them are daily active, and let's say each user has 10 chat service spaces. So there should be 2 billion chat spaces. And let's assume each chat has 100 byte. In this case, because billion corresponds to wait, so this is billion. So, wait a minute. So wait, I'm a bit confused. Kilobyte is 10 to the 6. Gigabyte is 10 to the 9. And this is million, this is billion. This corresponds to 200 gigabyte. So this should be 20 billion. So this should be terabyte. Yeah. Wait, so billion is 10 to the 9. 2 times 10 to the 12 byte. So this should be 4 times rounding up. So kilo, mega, gigatera. So 20 terabyte. Okay, so this is completely storable. I mean, this can be put on a single primary DB, I mean PostgreSQL primary node, because nowadays one database like AWS Aurora can store 256 or maybe 500 terabytes of data. So this is completely affordable in one primary node. But of course, considering the availability, or I should say scalability of the reads, maybe we can do add the read replicas here. Okay. So this is user chat relation table. Now we'll talk about the biggest problem here: message delivery and message media metadata. So I will talk specifically about the message because media is kind of optional. So most of the message doesn't include the media. So I will talk about message and message delivery is created per user. I mean, for each message delivery record is created for each user in the same chat. So this message delivery is bigger, of course. Yeah, and also because I did the redundancy here, this has a whole attribute, almost whole attribute of message breakout. So definitely message delivery is bigger. So I will talk about this. So let's assume one message is 1 kilobyte because it has the text. It can be wrong. Yeah. And let's assume okay. So let's assume one user sends 10 messages per day. So there should be 10 billion messages per day. And let's assume each record is 1 kilobyte. Then 10 billion is, so this is 100 terabytes per day. Yeah. Wait, am I correct? This corresponds to gigabyte, terabyte, 10 terabyte, I think. Yeah. So maybe I was wrong here. 100. This is 10 to the 20 billion is kilo million billion times the 9. Yeah, this is correct. So this should be 2 terabyte. Yeah, and this should be 10 terabyte. Okay. Yeah, so this means that, yeah, this is huge, and we have to store 30 days of data, which means a 300 terabyte of data in a month if nothing is read and this post message deletion worker doesn't delete anything. So this is huge, but thanks to DynamoDB, because we set user ID as a partition key, I can think the message delivery record which belong to the same user are on the one server. So with this estimation, one user has 10 to the 30 is 300 messages per day. So 300 times 1 kilobyte, which is 300 kilobyte. So thanks to the DynamoDB's partitioning, I can think that in a kind of extremely situation, I should say, one DynamoDB virtual node stores 300 kilobyte data only. And if there are many virtual nodes in the physical server, DynamoDB moves the virtual node to another physical server, so this doesn't become the issue. Okay, so now I talked about the storage scalability. Okay, so now I will talk about the next topic. Yeah. This one, how to support multiple devices for the same user. So this is quite intuitive. I can create device table here in primary DB, and we keep which user, we also of course persist which user this device belongs to, and maybe we need registered at, or I should say logging at timestamp or something. Yeah. And with this, what happens is that when user sends a message, okay, so this user now becomes a device. So for each device which is online, the message is delivered through WebSocket. And also, about this message delivery, this now becomes device ID. So we can make sure which device the message should be delivered. Yeah, so that's the thing. But one more thing I have to take care is, because we use the DynamoDB, there is a number of records to be updated in the same transaction. So here, when the message is sent, real-time message server creates the message record and also message delivery record too in the same transaction. But now, because there is one message created, there are up to 99 message delivery which can be created. This is an issue because let's say each user has 3 devices, only 30, we can include up to 30 users in the same chat room. But think of the university class, there are more than 50 or 60 users in the same class. So this limitation is very inconvenient. So I have to think of the way how I can do this without using the database or DynamoDB transaction. And the answer is, what I talked yesterday is using the queue. So instead of updating the medium metadata here immediately, here I create message metadata asynchronously. So I would say I use delivery message queue. So here, this message service creates a record here, and there is a worker who creates the delivery record to the DynamoDB. And maybe we can even make the creation of message record with this. Oh, no, I can't. Yeah, I should do only the creation of message delivery, because when we'd like to make sure, because I can expect almost 100% durability of message queue when this real-time message service publishes the message into the message queue. I can almost think that the data is persisted. So I think it is even possible that we completely don't do this, but instead worker creates the message record as well as message delivery record. Yeah, and of course this worker, even if this fails, this message delivery can be created. So in the end, with the retry, I can kind of expect the eventual creation of this message delivery. So this is good. But there is only one problem here, because the message is delivered so quickly to the device, and device, at the next moment, device acknowledges the message. Oh. So it is possible that this acknowledge call, when this acknowledge call is made from, when real-time message service tries to update the acknowledged add in the message delivery table, this message delivery table is not created yet. So maybe this is too early, this acknowledge something. So what I would do here instead is I create new queue named acknowledge queue, and now when there is acknowledge from the user device, this real-time message service pushes into the acknowledge queue, and then there is another worker here which updates the database acknowledged at column. So this subscribes acknowledge message queue and write it into the database. So I think this is something I can do. So maybe I can kind of specify the delay of this worker to write the message. There should be some delay. I can specify the delay that worker fetches a message and then create the acknowledged at record. Maybe this worker can wait for maybe 10 seconds before it updates the acknowledged at. In message delivery table, or even if something fails the worker, of course this worker can retry and finally update acknowledged at column. So I think in this way we don't have to use the transaction of the DynamoDB. So now we are free from the 100 record update in the same transaction limitation from DynamoDB. Okay, that being said, I finished my today's practice. I talked about two things, scalability and multiple devices support. Yeah. From tomorrow, I will talk about these topics. Okay, thank you so much. Bye-bye.